All right, so this is a recap of the activity 2 electrostatic force. We are going to work on the first CER, the electrostatic force and quantity of charge between two objects. This is kind of important, two objects. Keep the distance the same here. Do not move the charges. So we're going to use a simulation to show what happens when the electrostatic force, or what happens to the electrostatic force when one or both charges is zero, what happens to the Fe when one of the charges is increased, and what happens to the amount of Fe the charges feel when just one of them increases. So here we go. All right, so this is the Coulomb's law simulation that we have in our packet, and I wanted to just point out what the website was. So employees one onta.edu, and then all the slashes that and stuff that comes after it. So we're looking for what is the electrostatic force when one or both of the charges is zero. So we can find that right here where it says force of attraction. Right, so right here where it says force of attraction, let me see if I can get the pen to work. Okay, right here where it says force of attraction. Doesn't seem to be working, so we'll just keep going. That's what we're looking for. That is our electrostatic force. So we're going to make the stationary ion, which is the red one, we're going to make that 0. And then we're going to keep the mobile ion at -1. What we end up seeing is that the force of attraction is now 0. All right, so we're just going to go ahead and type when one or both of the charges is 0, the electrostatic force, which is the Fe, okay, remains at 0, or 0 newtons. And now we're going to address the second question of what happens to the electrostatic force when one of the charges is increased. So we're going to go back to increasing this. Now it's at +1. And so we have our force of attractions at 3.7 times 10 to the -9. And our distance is 2.5 A, which stands for angstroms. It's a unit of measurement. Because these particles are so small, we don't want to use meters or centimeters like we've been using in class. And so what we're going to do is just increase this +1. We're going to make it +2. And we see that this number changed. So let's go back and see what that looked like. Let's see if we can get our pen to work. Okay, great. So we had 3.7 first, right? So we had 3 point. I'm not sure why it's not working. I'm really sorry about that. Okay, so it's 3.7 times 10 to the -9. And we're going to see this number. Let's go ahead and increase this one. We're going to make that +2. And let's see. Let's see if we can get it to work. Okay, I'm going to pause this right here. I was able to get rid of the pen mark, so we're going to turn +1 into +2. And now we see that this has become 7.4 times 10 to the -9. We see now that the, before it was at 3 point something, right? 3.7, and now it's become 7.4. So when we doubled the charge in the stationary ion, it looks like our force of attraction also did something. So we're going to go ahead and answer the second bullet point, which is, let's see if we can move the screen over. All right, so when one of the charges is increased, the electrostatic force also increased. When both of the charges were increased, let's take a look and see what happened. All right, so when we say increase, it doesn't mean that the -1 will become a higher number. So like 0 would be a bigger number than -1. It just means that the magnitude is going to be much bigger. So we're going to increase both. So now one's at +2, the other one's at -2. And what happened to our number here? It was at 7.4, and now it becomes at 1.5 times 10 to the -8th. Remember that when the smaller number, or when the number is decreased in the exponent and it's a negative number, that means it's getting bigger. So our force of attraction also increased. All right, so we're going to go ahead and type that in. When both of the charges were increased, the electrostatic force also increased. And now we're going to go and answer the third one, which is what happens to the amount of electrostatic force the charges feel when just one of them increases. All right, so we'll take this number 1.5 times 10 to the -8th. We will increase the stationary ion, and we see that the number is also increased. So the number has increased from 1.5 to 10 times 10 to the -8th. And then if we go back, where we had -1 and a +2. So we had our 1 here, 3.7 times 10 to the -9th. When we increased it by 2, it went to 3.4. Now, if you see that we went 1 to 2, our value doubled, and our value also doubled here. Now let's go ahead and write that in our claim and our evidence. All right, so the amount of electrostatic force, Fe, the charges feel when just one of them increases. So when we doubled the stationary ion, when we doubled the charge of the stationary ion, the electrostatic force, so that's our Fe, also increased, it increased by 2 times as much, so it will say that it also doubled. All right, so now in our evidence section, we saw that this happen. So let me go ahead and put, so the stationary ion, so number 1, the stationary ion here was, let's see, stationary ion, and had a little force, was +1. And then we'll make our, oops, that's really thick. And then we had our mobile ion here, which was -1. Now when we turn this to become 0, so we'll go ahead and erase this. When this was 0, that means that we actually didn't have any force, so there was no force. Okay? So no force. And then when one of the charges increased, so let's go ahead and make our stationary ion went from +1 to +2, and we will keep our mobile ion at -1. Okay, we saw that the electrostatic force went from 3.7, I believe, times 10 to the -9th. Okay, so that was at 3.7. And when we changed it to +2, it went up. It went to 7.4 times 10 to the negative 9th. I should always use my units, newtons. And so that is your claims and evidence for number 1.